Good morning, everyone. I have to switch from good afternoon to good morning. Welcome to the first lecture of spring semester of 2016. Happy New Year to everyone. And I'm very happy to introduce today's first speaker, Professor Martin Starzewski from the University of Illinois at Urbana-Champaign. Martin got his first degree in Krakow, Poland. Then he got master and PhD degree at McGill University in Canada. After that, he worked in a number of US universities, Purdue, back to Canada at McGill. And for the last 10 years, he is working at the University of Illinois at Urbana-Champaign, where he is professor at Department of Mechanical Science and Engineering. And his area is random media in material sciences. And with that, I would just give Martin the podium. And please join me in welcoming the speaker.
Thank you very much, Sonia, for inviting me here. I understand this is the first seminar given morning time. So you're using me as a guinea pig to give an underground seminar. Famous building that I heard about many times ago, many times. So I will talk about some issues in mechanics of random media, starting with the problem of passage from a random microstructure, such as here some matrix inclusion composite with random distribution of inclusions, to a homogeneous continuum. And this is what we want in continuum mechanics, conventional continuum mechanics, some continuum model which hinges on the concept of representative volume element, RVE. And so this is the same thing as the dV element in continuum mechanics, over which we postulate that we can take gradients and such when we localize balance equations. So continuum mechanics really hinges on this concept of, or postulate, of separation of scales. L macro is the macroscopic dimension. D is some microscale. And definitely we need this first inequality here to have some differential equations going on. And then we typically see this second inequality here written more or less in a qualitative and speculative way. I say speculative because it turns out when I will be doing micromechanics that one actually does not always need to have D much less than L, but just less than, maybe five times smaller will be sufficient. So I'm looking at homogenization of microstructure, actually a sum realization, so everything is deterministic, to a continuum type random field. Mesoscale, so meso from Greek meso means intermediate. And if this window is not large enough, then we'll have fluctuations seen here. But if the window is large enough, then we won't see those fluctuations. Depending on the situation, perhaps here we'll have to deal with a random field of, say, material moduli as opposed to constant field, non-random. As a paradigm of this, one can think of a sheet of paper held against light. And what we definitely see here right away is the grayscale fluctuations in opacity because of formation of paper. Formation of paper, that's the term used in the paper industry, and all the paper makers strive for making a homogeneous paper sheet, which is impossible. First of all, because of flocculation effects, formation of flux by electrostatic forces during paper making process. And secondly, even if there was no formation of flux, then there's no way to uniformly make a medium made of random fibers. I mean, varying lengths, widths, and so on. As I look at this, I see a random field. As I pull it away from my eyes, depending which one, bifocal vision right now at this age. So, but my left one is pretty farsighted. So I pull it away, and the field changes. It homogenizes. And I know you don't have a next building here. I always say to students, if we put it on the wall of the next building, then it would be homogeneous continuum. But what I'm getting at is that this one realization of a random field is really scale dependent. So it's not unique. it's a bit dangerous to say that we have just one continuum random field and that's it. A continuum random field depends on resolution that I have. A resolution here would be dictated by this window. So that's something to keep in mind. And this then is definitely needed as input into stochastic partial differential equations, all kinds of stochastic field problems, waves in random media, stochastic finite elements, and the list goes on, stochastic plasticity, and so on. And a classical problem in mechanics, stochastic mechanics, is to ask what's the difference between doing a homogeneous medium problem and getting this one solution versus a random medium problem, which means getting a distribution of solutions and then taking the average, ensemble average. How different is the average from the solution of the problem which is homogenized right away a priori? So this is what all stochastic mechanics people want to do, and always they want to arrive at a result. You see, if you homogenize too early, you're wrong. So here is a kind of a basic field equation written symbolically, but we can think of it as a Navier equation of elasticity. And there are three ways of introducing randomness. One is through forcing. So then this would correspond to something like random vibrations, where we have an oscillator. There's nothing random about the spring and damper, but random forcing is random in time. Another possibility is to introduce randomness through boundary conditions, whatever boundary conditions, displacement, traction, mix, and so on. And the third possibility is to have randomness in the operator itself. It's like saying that the Lamé coefficients are not constants, but are random fields. So this is one of the things that motivates me here. Can we even say that we have Lamé coefficients, or would it be more honest to admit the whole anisotropy of the stiffness tensor? So basically, I'm working here under the motto, how big is big enough? This issue, and the classical micromechanics always goes for this macroscopic response here, whereas I will be describing a procedure which allows you to get moduli in function of mesoscale, and in the end we're going to get effective moduli of classical micromechanics, for example. So the way to go, I only see one path for handling inelastic problems, coupled field problems with some dissipation, and that's through RV definition due to Hill and Mandel. Hill in UK, Mandel in France. And the work of Hill is much better known, especially in the Anglophone world, but also because at that time in France, one first had to publish in French and get the permission from the government to publish in another language. But as far as I know, and I discussed it with friends in France several times, it was really done independently by two people, exactly the same thing. These words are taken from a 63 paper of Hill, and I translate it now into a more modern language. Basically, one is a condition that one needs a statistics which is homogeneous and ergodic in space, meaning that for every realization, the volume average is the same as average realization as the average at the given point in the domain. And the second condition is a mechanics condition. So one is a random geometry condition or random microstructure. The other one is the idea that the requirement that response under traction boundary conditions is the same as under displacement boundary conditions. And I call it mesoscale, and perhaps this is good enough to serve me as a DV element. So now let's write it. This is what they actually, what one does, and one writes 1/2 sigma dot epsilon scalar product, and I would write it. This is 1/2 sigma dot epsilon is equal 1/2 sigma dot epsilon. Then I take averages. One way to take averages is to average the entire, say, left-hand side here. Another possibility is to take the average of stress and average of strain separately. And this corresponds to the, I have dropped 1/2 because it's trivial. And this corresponds to a picture viewed by, or concept of a theoretician who works, say, typically with energy densities, and an experimentalist who will say, I don't work with energies in the lab, I work with volume averages of, say, stress and strain. I'm applying stresses, strains, and so on. So that's a handshake that allows me to set up a constitutive law in a consistent way, two different points of view. Then one uses Green-Gauss theorem a few times and balance laws, everything statics, no body forces, and one gets this condition which dictates three possibilities as far as loading. So three uniform boundary conditions. One is displacement, so uniform displacement boundary condition. Same thing as uniform Dirichlet or uniform essential or kinematic. So those adjectives keep on changing, and I sometimes keep on changing them as I talk. And the second one, clearly I can make this 0 if I make this piece of the integrand 0. So traction on the boundary is given as some sigma average, prescribed mean stress, and dot dot with n, so Cauchy concept. And there's a third possibility, so-called mixed orthogonal boundary condition, where 1 degree of freedom is traction, another degree of freedom is displacement. And this is less interesting right now, but perhaps we can talk about it later. But these two are very interesting because they provide bounds. This one from the standpoint of minimum potential energy, and this one from the standpoint of complementary energy principle, minimum complementary. So here's the illustration of bounds for random distribution of inclusions, actually anti-plane elasticity problem, which is of course same as in-plane conductivity problem. So sometimes I'm talking about conductivities here, but I'm looking at a situation where stiffness of inclusions, and they are isotropic locally, and so is the matrix, is 100 times greater than the stiffness of the matrix. It's like composite, which is stiffened by inclusions. And if I go with this Dirichlet bound or displacement control bound, or essential, I'm using here, E superscript, then I have this result for the trace. Strictly speaking, I have scatter. For any given window, I have to solve the problem by some computing method, finite element, finite volume, whatever your preference is fine. In principle, you have to run it in Monte Carlo, get the statistics. Actually, it's very interesting. One gets some interesting statistics. And take the average, and that's it. Trace, and one can get other elements of this apparent or mesoscale response. One has to do traction problem and do ensemble average first, then do the inverse of that, so I can draw it on the same axis. And we clearly see a trend where they become identical. In other words, the trend where one is the inverse of the other. Where is that going to happen? Well, mathematically, unless you have periodicity in the medium, which would right away define the RV, I have to go to infinity. And this is the way it works. So people ask me, so Martin, what do you propose for RV here? And I say the beauty is in the eye of the beholder. If you're willing to live with 10% error, you're saying here, if you want to have 5% error, you have to go here. If you want to have 1% error, you have to go somewhere else, further out. This is the way it works, and so this is a typical feature of this whole approach. If I go to contrast 10 to the power 4, so much stiffer inclusions, this trend is of course much slower. So here's where I hark back to what I said early on, that one cannot, one doesn't have to assume immediately that the size of inclusion has to be much smaller than the size of mesoscale window. For some systems, if contrast is weak, then perhaps 5 times bigger, you already get 2 bounds which are very close to each other. But if contrast is very strong, then you have to go to large windows. And the situation changes if I go from stiff inclusions in a soft matrix to soft inclusions in a stiff matrix. Here's a case of inclusions being 100 times softer. So this is the behavior of Dirichlet. Here's Neumann. And here's 10,000 times softer. And if I go to 10 minus 4, then it's almost horizontal, and 10 to minus 12, 15. It's a situation of Swiss cheese, how to homogenize a plate with holes, at which point the method breaks down, basically because the method doesn't work for phases which are not elliptic, strongly locally elliptic. And one has to go to some effective medium theory, like Mark Kachanov is using Mori Tanaka for those problems. And here are so-called banana plots, just a quick story. These are very popular in the 80s and 90s when people were doing effective medium theories. Here I have a random checkerboard, which we very often do because it gives an idea of how things behave. And here is the void bound, linear. Here's the Royce bound, the harmonic mean, right? And here's the Hashing-Strickman broken line, Hashing-Strickman lower bound. But if I go with windows that are 4 times bigger, I have circles, 10 times bigger or the better, and 20 times better. But to get a unique line, I mean, overlapping of both bounds, I would have to go to infinity. So the nice story about this is that the approach is initially very quick of both bounds, and then they begin to asymptote slowly. And there's a situation, for contrast, 100 in the checkerboard and 1,000. Of course, it's a function of volume fraction, right? So, on the theoretical side, one works with energy density or complementary energy density, and one has this hierarchy of scale-dependent bounds, where at the very, very end I have the void bound, okay, and at the other end I have the Royce bound. So these are straightforward averages over on the scale of just 1 grain. And if you have a 2-phase medium, then you do it on the back of envelope, 2 lines. And but if you take bigger windows, then no way. You just have to do some problems on a computer, but perfectly doable. So these are qualitative bounds. These hierarchies, the monotonicity is proved by combining principle of minimum potential energy with assumption of homogeneity and ergodicity of spatial statistics. So one has to marry 2 properties. And here one uses complementary energy principle. And so I already talked about ellipticity. And one can use this approach to 3D random polycrystal. I'm showing just one realization, 8 cube grains, where randomness consists in orienting every grain isotropically on a sphere of orientations per each grain, in a white noise sense, so everything is uncorrelated in space. One could do spatial correlations also, and then the trend to homogenize to RV would be much slower, depending on what correlations you assume. So here again, here's void bound and Royce bound, and here are those Dirichlet and Neumann bounds. Here's the hierarchy, and I already mentioned that in the limit, when I go to RV, this one should be the inverse of the other one. So this motivates us to introduce a scaling function. Let's just focus on the last line here. So on any mesoscale, I have some discrepancy, some deviation or departure from this limit, which is the conventional continuum mechanics limit. And so this is a scaling function. So that's very nice because one can set up the whole scaling behavior in terms just of a scalar function in terms of a scalar mesoscale. So that's coming up here. We did various polycrystals, copper, lithium, tantalum, and so on. All of them like that, but they can be mapped onto just one curve, which follows the stretched exponential form. So that's basically a universal behavior for many of those scaling laws. So physicists are happy with me when they see that. Yeah, you nailed it down to just one function. So even though one may have different materials, but in the end, there's something universal coming out of these things. And one can also talk about the behavior of statistics, say probability density of properties. If I sample with window size pointwise, then I either hit black or white phase. There's 0 probability of hitting the interface, which is undefined property. So then I have 2 Dirac deltas for inclusions in matrix whose strength corresponds to volume fractions, right? But if I sample with a window which is somewhere bigger than a mathematical point, then there's some chance that I will sometimes hit the interface. So then I'm looking at probability density, which is bounded by these 2 Dirac deltas. If I sample by window which is even bigger, then I will always have some inclusions inside, and probability density becomes kind of bell-shaped, but not Gaussian. It's bell-shaped between these two. So natural model for this from statistics is a beta probability density, which represents this flow of probability distribution, or probability density, as I change the scale. So there are various results like that. Here are a few words about Elasto-Plastic, random composite. So we're looking at inclusions, again at random, just one realization, following some Ramberg-Osgood hardening law. So inclusions, matrix is hardening, and inclusions are always elastic. So up to this point, there's nothing interesting going on. If I load up to this point, material doesn't even know about the yield, right? If I go beyond the yield, if I go beyond the yield point, the question is, what is the effective response? That's the classical question of micromechanics, and I'm asking even more, what are the bounds like? So yes, we can bound it. We'll set up boundary value problems for elastoplasticity, where plasticity is taking place in the matrix, and inclusions are acting as obstacles. So here is this the stress strain curve of the inclusions, which are obstacles, and here's the matrix, and here's the Taylor bound, so uniform deformation rate assumption throughout the body, analogous to Voigt assumption. Here's the Sachs bound, uniform stress assumption, and then there are bounds that stem from windows which are 6 by 6, 20 by 20, and so on. So this gives an idea how well one can approximate or can get effective response when one gets very nice bounds. And the results of some boundary value problems that were involved here on scale 6 and on scale here 15. I also show, actually if I back up, one can see that even though the traction is uniform, prescribed in a uniform way on the boundary, the displacement itself is non-uniform, right? Whereas here, the displacement is linear, affine displacement, but the traction is fluctuating. And so we're interested in this limit where the fluctuations become so minute, right, the asymptotic limit. And but before that, we have a random medium, and perhaps my finite elements in the macroscopic boundary value problems are cut to this size, then I must not assume homogeneous deterministic response per window, but random responses. And actually, shear bands, since they go in the matrix, they follow a geodesic path. So they have geodesic property with good approximation, but not perfect. We use this type of approach to also study the problem of RVE of paper, because production of paper is actually very interesting. It's a paper web on modern paper machines, 10 meters wide, coming out of paper machine at about 100 kilometers per hour, or 62 miles per hour, which is a huge machine, about a mile long, very automated and so on. Initially, the suspension of paper comes in at a low speed, and the whole thing is being stretched and stretched. The water is being squeezed out by rollers, and in the end, one has those flux in the paper, and on a machine-made paper like that, there would be some anisotropy. But what people are interested in is mechanics of a web flying and fluttering in the ambient atmosphere. So here we have typical flux size is 5 millimeters, and we can look at paper as a superposition of many fuzzy disks, and so that's where we're using like a disk overlap model, and then the stiffness local is proportional to the number of disks at a given point. We homogenize according to those Dirichlet-Neumann boundary conditions, and we get basically the result that paper can be regarded as homogeneous with this type of error on a scale 10 times bigger than a flock, which means 5 by 5 centimeters. If I want to have weaker noise, I have to go, say, 10 by 10 centimeters, 20 by 20, and so on. So one can get results of that nature out of this. A few more words about elastic plastic materials. So I have already talked about this issue, right? And but then another interesting issue is what about the yield surfaces? Suppose I know that each component phase follows the normal flow rule of plasticity. Where is the effective yield surface and what's the flow rule there? If both components, constituents of the composite, follow the normal flow rule, does it assure that the flow rule of the random mixture is also normal? And so this type, and one can get this approach towards effective yield surface of the idealized homogenized elasto-plastic material in terms of those bounds. So there's a hierarchy of inclusions which I can write. Now, not inclusions in terms of the stiffness tensor and compliance that I showed earlier, but in terms of yield surfaces which contain ever smaller regions. Right? And so this is shown up here. This D-effective or D-infinite on infinite scale under displacement boundary condition domain, which is the same thing theoretically as the traction controlled. And then if I go to larger to smaller domains, I have this containing sequence of under traction controlled and here displacement controlled. But now coming back to the problem of normality, even though both phases were assumed to follow normal flow rule, and we did it by finite elements and everything, clearly I have a departure from normality here. It's like 80-something degrees, and not 90 degrees on finite scales. One can apply this approach also to finite elasticity of random media. And so we know from continuum mechanics that there are various conjugate pairs of stress and strain measures. And luckily, there's one pair which is behaving nicely. And there's the pair of first Piola-Kirchhoff stress tensor and deformation gradient tensor. And they allow us to write this uniform, kinematic uniform boundary condition in a linear way. Whereas if you take like second Piola-Kirchhoff, doesn't work, and so on. So it's very interesting. There's one good pair to work with. And so, okay, so this is a generalization of the Hill condition, which then one has to combine it with minimum potential energy and complementary energy formulation that's due to Lee and Shield. I was happy that a few years ago I found this paper. And then one can prove a sequence of the hierarchy of bounds, which are now written in terms of energies. I don't have stiffness compliance tensors, of course. I just write in terms of energies. And so here's an example, Ogden inclusions in a neo-Hookean matrix. Here's Ogden inclusions, and here's neo-Hookean matrix. And we subject windows, for example, like this one, to traction boundary conditions where traction is uniform. Believe me, it is uniform. According to first, we control the first Piola-Kirchhoff tensor. But the displacement comes out very non-uniform, this large strain situation. So actually this can also be extended to thermoelasticity, even finite thermoelasticity and so on. So for this particular situation, we got the result that on the scale of 16 by 16, larger than the grain size, the results from displacement and traction boundary conditions were almost overlapping. So here we go. This is kind of an estimate of RVE size. One can apply it also to viscoelastic materials. So we write constitutive laws, say, for two-phase material like that, where there would be a difference between R function for black and R function for white, and so on. Or rather than working in time domain, I can map it, go into working frequency domain, and ask the same question: what's the trend to RVE? And so there's a modified Hill-Mandel condition due to UA some 20 years ago, which involves, which dictates then these kinematic, what he called KUBC, kinematic uniform boundary condition, and static uniform boundary condition. And static, I mean, is changing in time, but very slowly. Everything is quasi-static. And so then here's an example of what comes out, and one can get bounds on viscoelastic response with some numerical values for a particular mixture of components. One can do this type of thing in a frequency domain, and I'm showing here only a complex shear modulus, absolute value and phase angle, and everything has those consistent behaviors. There's no crossing of bounds, nothing, everything goes like that. And once the numerical work is done on a PC, then one basically has a description of a random viscoelastic material in function of scale, because this is the mesoscale dependence. And, so, of course, one can back out here the effective response with good precision. And we actually went for the scaling function because the whole problem kind of should be analogous to linear elasticity from linear viscoelasticity. And lo and behold, we got the same form, stress exponential, of the scaling function here again. For various kinds of combinations, various kinds of material systems. All of them, in the end, can be mapped onto one functional form. One can also play this game for homogenization of a heterogeneous material by non-Cauchy material of higher order, where, so we know that classical continuum is primitive in the sense that each and every point only knows about displacements, translations, doesn't know anything about the micro-rotation. But if we admit those micro-rotations, then besides the Cauchy stress, let's say strain, here I talk about small strains, I will have the coupled stress tensor and the curvature torsion tensor, kappa. Yeah? And so kappa and mu are dual to each other. So here's the Hill-Mandel condition, sigma, then there's a mixed term, and then there's mu kappa. Actually, this sigma, because in general, the Cauchy stress is not symmetric, it's mu. But then I go and use symmetric part of the non-symmetric stress, so there's this extra beta. So it's a bit messy, but in the end, one can formulate kinematic boundary conditions, where, first of all, we have classical kind of extension, dilatation into the shear. But Cauchy continuum doesn't know anything about curving, twisting of material this way. And so those conditions have to be set up in a computer model. Then you apply this to a computer model, do it many, many times in the ensemble sense, get the statistics, and one can do the same type of thing for stress boundary conditions. And then one gets bounds on the responses of the Cauchy continuum. And so this is very popular in Italy because of concern with ancient structures that are made of blocks and sensitivity to earthquakes. So actually there's joint work with Italians, which is difficult to conduct experiments, but it immediately makes sense that a better model for a blocky kind of structure is not Cauchy but Cauchy type of material with rotational degrees of freedom. And then, of course, one can use it as input into boundary value problems. And there's different solutions, say, for elastostatics of Cauchy versus elastostatics of Cauchy. So overall, we have this Hill-Mandel condition, which, like I discussed, gives possibilities to evaluate linear or nonlinear thermoelastic responses, rigid plastic, I didn't show, elasto-plastic, hardening, viscoelastic, also permeable and poroelastic. If there's time, perhaps I'm speaking too fast, then I can discuss these a little bit. And one can also do dynamic responses, so strain rate dependence. This would be this. We already have an extension of Hill-Mandel condition for dynamic loading, which involves kinematic energy. And then non-Cauchy materials, I mentioned that. And this serves as a formulation of what I mentioned in the beginning, formulation of tensor-valued random fields. which should provide input into, say, stochastic PDEs or stochastic finite element methods. And the latter ones are typically based on the assumption, well, let's take the global stiffness matrix as mean plus some fluctuation K prime. And postulates of this type, or let's just randomize Young's modulus throughout the domain. And I submit that one should do those things from micromechanics point of view. So overall, we have convergence to RV that depends on elastic versus inelastic. And we always get the result, and also other people working on those topics, a result that elastic homogenize faster than inelastic, or nonlinear. There's a dependence on the mismatch. I discussed that. There's dependence on microscale geometries. One can go into all kinds of problems, having disks versus ellipses versus spatial clustering, and so some correlated structures. One has, for linear elastic microstructures, I spent some time discussing those, the convergence of moduli for stiff matrix with soft inclusions, or the opposite situation. But actually, convergence to RV is slowest in anti-plane elasticity, is faster in in-plane elasticity, and fastest in 3D elasticity. And the way I understand it is that the kernel of the elasticity problem in 3D has different form than the kernel in 2D or anti-plane elasticity. So anti-plane is kind of quickest to program and quickest to run, but in the end you have to run bigger domains. So there's the various trade-offs. In problems without separation of scales, one needs to work with random fields and solve just stochastic boundary value problems, which typically are done. So you look at typical mathematics texts, stochastic PDEs, just assume some random fields of Lamech constants, coefficients. And a recent topic that I'm working on, I don't know, we have a few more minutes. In case the pore sizes are very small, so you're reaching down to nanoscale level, one may have to account for violations of second law of thermodynamics in the flow of fluid on those very small scales. So I don't know, we can either discuss this subject, I will discuss what I talked about, or I can go and talk a little bit more about results, whatever you prefer. Because I was warned that I have to end by 11:10 exactly.
We have 5-7 minutes here.
Yeah, so here formally, no, I will. Here's the flowing porous media problem that may be of interest. So locally in the channels we have Stokes flow, that's classical continuum fluid mechanics, but macroscopically, as far as permeability, we have this purely phenomenological Darcy's law, which doesn't even make sense if there's no suspension. So it's just a phenomenological assumption. Very nice, very useful. And but I have the mathematics which suggests that I can work out these problems providing I find the Hill-Mandel condition. And so this is shown here. Pressure gradient is conjugate to velocity, fluid velocity, overall fluid velocity. And so there's two ways of averaging, either volume average of this pressure gradient with velocity, or separate. So this is, again, the experimentalist point of view. So then, again, very quickly, I mean, just by analogy to previous results, we get this. But very interestingly, there's a gradient in pressure here, and velocity, no gradient in velocity showing up. Whereas in other problems in elasticity, we have gradient of displacement, which is strain and then traction. So the roles kind of are interchanged now. So so I have a Dirichlet problem, which is then controlled by mean pressure gradient, mathematically corresponds to like mean strain, and velocity problem, boundary value problem here. And so one can get, again, a hierarchy of bounds on effective macroscopic permeability, say KF, or resistivity 2-1, and from above, from below. And so here I'm showing some particular result for round disks occupying 40% of the entire space. Everything is in 2D. And Here I'm collecting results for various material systems, actually using this scaling function idea, namely looking at scalar product of K with R, which if medium is homogeneous, it should be 1. But if medium is not homogeneous, it will be greater than 1. So here's the scaling function again. For basically, the denser the system, the quicker the approach to Darcy law. Is consistent with intuition. So this. And now I will say a few words about the Couette flow. A few years ago, I found that physicists are working with violations of second law of thermodynamics. So I was initially flabbergasted. And then I started reading this. And actually, there are 3 typical material systems where they are looking at this. And so the first one is mechanics of molecular fluids. The second one is heat flow. Namely, heat ever so often can go in direction completely counterintuitive. And the third one is electrical systems. And I will try to show it through a molecular dynamics simulation using lamps. I know that I have to. I somehow cannot get this movie to run. Maybe it has to do with being underground. But what's happening here, I will say in words, the bottom plate is stationary. So in classical continuum mechanics, fluid mechanics, we know bottom plate is stationary, the top plate is moving, we have a gradient in velocity, a classical picture. Here I have a molecular fluid, particles are bouncing off and so on, and I have a so-called Lees-Edwards boundary condition, meaning that the top plate is moving and this rhombus is changing. And particles are flying. I have periodic boundary conditions between right and left sides. So whatever flies out here re-enters here. So this is changing. I will just see a movie. I'm pulling the top plate at a constant velocity. Therefore, my deformation rate is constant. Now, a conjugate to the deformation rate is the Cauchy stress. Cauchy stress comes out from simulation. Cauchy stress is not only fluctuating, but it's fluctuating because, first of all, the system is very small, so there's fluctuations in the system. But on top of it, ever so often it crosses 0. Completely counterintuitive. So Cauchy stress is fluctuating like crazy. Every so often it crosses 0. I say counterintuitive because our intuition is formed on the macroscopic level. Right? When we take a bath as kids and so on, we develop intuition with macroscopic physics. If I increase the window size, the channel size, and do exactly the same problem on larger scales, so I again have maybe this one I will be able to activate. I don't know, perhaps because of connection. Same type of thing. So this is done differently. The top plate is moving at a constant velocity. You have periodic boundary conditions left and right, and they are bouncing off and so on. Here's a system with a few thousand particles, and here fluctuations are very weak. So now let's see this system here, where I have a very small channel, strong fluctuations. The stress is crossing the 0 level, the green line, ever so often. If I go to a larger system, the chance, the probability of crossing the 0 level is smaller. If I were to go to even bigger channel, even smaller. I go to a system of a few thousand particles, it will hardly ever go through the 0 level, meaning become negative. This is in the same vein as Maxwell's demon, namely that what's the probability that all the particles in the room concentrate in one corner? Yeah, this probability is finite, but it's so minute that in order to get it, we would have to wait, according to statistical physics, longer than the age of the universe. So we'll not observe it. But if I run this problem of a chamber with a bunch of atoms in a small chamber, say 100 particles, yeah, I will see the situation that all the particles will be in one corner. If I do a bigger chamber with a few thousand, smaller chance, I will have to run it for a very long time. They will do it. So we have those violations, meaning that one wing of the distribution is actually turning out to be very much Gaussian always. And of course, one has to take it with a grain of salt because you know that plus minus infinity is not really possible. But so one wing is crossing the zero. One wing is crossing the zero. However, if I go to an infinite size system, the Gaussian tends to Dirac delta. There's no wing to cross the zero. It just becomes Dirac delta. Everything is Dirac. So this is basically the whole story, which is expressed here through a celebrated fluctuation theorem developed in '92, published in Physical Review Letters. And since then, there's avalanche of papers in physics on those issues. So here's this, again, Gaussian that's written differently. And since this was from a physics paper, they work with a pressure tensor, which is the negative of the Cauchy Stress tensor. So they have this wing, which is crossing zero. The probability of being by some amount on this side of the zero is smaller than probability of being on the opposite side of zero. So this is the ratio of probabilities. Fluctuation theorem gives us the ratio of probabilities of violating versus non-violating. And this is E2 minus AT. The longer you wait, the smaller the chance. And the larger the system, the smaller the chance. What this gives, the fluctuation theorem, is an estimate of relative probability of observing processes that have positive and negative total dissipation in non-equilibrium systems. It's a ratio of probabilities. It's very interesting. And here I take verbatim from a paper, a very nice review paper in Advances in Physics. In either a large system or long time limit, the steady state fluctuation theorem predicts that the second law will hold absolutely and that the probability of second law violations will be zero. So there's no, overall, for a whole system, there's no violation of second law, but locally there may be. There may be some negative behaviors which are completely counterintuitive to us. So the way I see it is that if one has a poromechanics problem with fluid flow, and then one has to be careful about those types of violations because ever so often the flow will go in completely different directions than you think it will. So at this point I will stop. Thank you very much.
Thank you very much. We have time for questions, and we start with random, which is no surprise.
Your Hill condition, you're focusing on averages. As an engineer, seldom do I care what the average behavior is. What I'm interested in is the probability of some condition occurring either locally or larger than locally. And your entire approach, I don't see how to take that and do the computation in the, or how it informs that computation. Probability of some event occurring, locally exceeding a stress, a strain ever exceeding some limit, whatever. That to me is more interesting in terms of, let's say, designing something.
Yeah, so Hill condition is stated for volume averages.
Yes.
For one realization, if I do it over ensemble, then I have statistical averages on top of that. So first of all, I do it for a typical element of the ensemble. And one can study this just for one typical element, ever bigger windows, boundary value problems. And then in principle, I have to do Monte Carlo or something, or maybe theoretically something is possible. But certainly, I think in civil engineering, you're interested in statistical scatter, and I don't quite get away your second point.
I'm not interested in averages. I'm interested in particular specific conditions, and I'm interested in the probability of some condition occurring.
Yeah.
So maybe I am. Maybe I just have to do Monte Carlo, and that's the only way to deal with it.
Yeah, so what this gives is a scatter of constitutive responses. Because first of all, if I do this problem, say 200 times in Monte Carlo sense, then I have a histogram. I can model some probability distribution. I can invoke some theoretical, say, beta distribution concepts. So that's very useful, I would say. And then I say that this is a stepping stone for stochastic finite elements. Because if I have a macroscopic body, I cut it in pieces. Then unless I have separation of scales for a given finite element, then I better have a probabilistic law here, constitutive law. Thank you.
Okay, more questions?
Could you comment on how one should use effective moduli in solving problems? How should one use the effective moduli? I mean, you were after getting effective moduli.
Yeah.
And my question is like, okay, should I put those in the equations of motion, those effective moduli, and solve problems with those? And how should I interpret the solutions of those? It's always been a wonder to me how to do that. I think this has something to say about the first question that was asked.
Right.
You know. I know that you're after much more than effective moduli, so I understand that.
Okay, here we go. All right, so, I have to do. So my answer is if I do a problem without body forces, so no elastodynamics, because elastodynamics puts in another wrinkle the wavelength. So we can discuss later. But if I do static problem, effective moduli would be good, providing I don't have any very sharp corners or geometries like that, because they're locally, I would really have to look at this, those particular geometric effects. Then suppose L is much smaller than L macro, then everything is fine. But if I have a material piece with, for example, 1,000 grains that way and 800 grains that way, and the Hill-Mandel condition tells me that I have to go to a window size 200 to kill the noise with error, say 5%, then I don't have separation of scales. So I'm saying that this is quite important for all problems of the type, which could be microtechnology, nanotechnology, geophysical problems, geomechanical problems, and so on. And of course, those mean moduli will not tell me anything about scatters. So we should always use, I mean, classical continuum mechanics is very nice. Just be careful about what it means when we apply to some polycrystal with 1,000 grains where the noise is still present on this scale. And we have done some problems. Kind of there are two competing trends. One trend is finite element trend. With finite elements, you want to have as many elements as, I mean, very fine mesh to resolve homogeneous medium. But if I have very fine mesh, then the mesh begins to see the microstructural noise. So there's the opposite trend to homogenization. I'm afraid I have not convinced you.
Sure. I'm not sure yet. Like, is there much done on these two problems of using the effective moduli and solving a problem, or using the equations originally and averaging them? You know, I mean, do the solutions tend to one another somehow? I mean,
yeah. So.
The solutions, not the energies. The energies, I understand, would tend to one another somehow, but the solutions somehow, is there some, probably not point-wise, they wouldn't tend to one another in the interior of a domain, but maybe on some average, I don't know.
Yeah, so I have solved a couple of boundary value problems inside out, which I think will sit later. I will show you in all detail.
Sure.
Right now would be too much detail.
Yeah, I understand. I'm just, I was just curious.
Sure, yes.
My question is probably a little detailed, but in addition to computing effective properties, theoretically, you can experiment as well for the problems which are heterogeneous. For large deformation problems that you showed, you are using first Piola-Kirchhoff stress tensor, and you say your stresses are uniform. But they are uniform in the reference configuration, that is not the distorted configuration. So if you compare that to experiments, you'll be comparing it completely differently, because in experiments you will be always referring to the current configuration, which is the deformed configuration.
I fully agree, yes. Yeah. In principle, one should map those problems again into, say, Cauchy stresses or something like that, purely spatial description. So in that sense, when I say experimentalist, handshake with theoretician is kind of conceptual. Yeah, on a friendly level.
You didn't discuss this in this presentation, but you mentioned that, of course, there is the problem of wave propagation, which has a whole different set of constraints related to wavelength. And there, I guess, the capturing of the dispersive characteristics of the medium is sort of what gives us the sense of how good of a job we're doing in homogenizing properly in a dynamic sense. Question is, do you see the dynamic homogenization for wave propagation problem a separate beast altogether that needs to be treated kind of separately, or it follows more or less the trends that you see in the static homogenization problem?
No, it's just a more general problem with an extra wavelength, length scale being the, say, wavefront thickness. I have looked at problem of propagation of wavefronts, which we know in continuum mechanics are modeled as singular surfaces, but in reality we know they are smeared over some final thickness. So then the problem that we can discuss later in more detail is the problem of acceleration of waves. They are governed by a Bernoulli equation, which is a competition of two terms. And now, if the wavefront is comparable to grain size, then moduli which come into the governing equations are random fields. So then the competition is stochastic for blow-up of wave format. Whereas if the wavefront is smeared over 100 grains, and Hill condition will give me an indication, am I kind of on RVE level? How strong is the noise? Then noise is irrelevant, the second depth. So this can be should be used as guidance.
I may ask some question. You introduced this scaling function to deal with randomness, and you showed some specific functions. Do you make some assumption on the way how this function is structured? What is the kind of
No, it's just the curve fit of results. It's kind of in the spirit of physics.
Okay.
You have a number of data which display certain behaviors in a very consistent way. Let's find a good scaling fit.
Okay. Thank you. Okay, if there is no question, we are almost used all the time, so let's thank the speaker. And remember, we have reception at 4:30 where you can come and ask more questions. Thank you.